Hello, Gregory Carlson here. We're doing section 3.4, part 2 of college algebra. Let's get to the intermediate value theorem. So the intermediate value theorem is really cool. It basically says, let's say we've got a function that's continuous, remember, so it's a function that we can draw without lifting up our pencil. If it has AB as an interval, so if we're, just as an example, let's say we've got some function that's continuous. And let's say we've got a value between A and B in our domain, then that means the graph takes every single point between those two values. So the graph, by definition, has to fill in all of the values between these 2 points. It might curve around a lot in the middle, but every single point will have to be there. We can't lift our pencil. An application of that is there's some tollways where the way they catch speeders is they time how long it takes to drive the entire length of the road, and they know how long it is. And so they time how long it takes you to drive it. And if your average speed is higher than a certain interval, higher than a certain number, then because of the intermediate value theorem, they know that at some point you had to have been speeding, or else you wouldn't have gotten there so fast. So even some police officers and toll watchers can use the intermediate value theorem to catch speeders. And so the way you'd get around that is what you would do is you'd have to take a picnic somewhere in the middle to allow yourself to be able to get a much higher average speed. A corollary of the intermediate value theorem is that if at some point you have a graph, and at some point the graph is negative, and at a later point the graph is positive, then if this is a continuous function, that means you need to have a zero somewhere in between those 2 points. It doesn't matter where it is, but it's going to be somewhere in this open interval. So somewhere in there you're going to have a zero. So that's called Boson's theorem, and it's a corollary of the intermediate value theorem. A corollary, the definition of that word is it's an important result that comes from a theorem. So here's the general case, but a special application of that is we can use it to find zeros. Let's look at an example. Is there a zero in this polynomial between -4 and -7? So if we plug in -4 and -7 and one is positive and one is negative, then that means because this is a continuous function, there has to be a zero somewhere in the middle there. So let's try that out. Let's see if my calculator skills have improved. -4 times -4 times -4 times -4 is 256. That will be -4 times -4 times -4 will be -64 times 4 is -256. 4 times 4 is 16. 16 times 11 is 176, so that'll be -176. And then 30 times 4 is +120. So if we add that all up, this cancels with this. -176 plus 120 is equal to -56. All right, that's f of -4, plugging in -4 into the function. Let's plug in -7. So -7 times itself 4 times will be positive, and it's equal to 2401. 7 times 7 times 7 is 343 times 4 is equal to 1372, and that'll be negative because we have 3 negatives right there. 7 times 7 is 49. 49 is positive times 11. We'll make it negative, -539. And then 7 times 30 is 210, so that'll be +210. So let's add all that up. 2401 minus 1372 minus 539 plus 210, and we get 700. So look at this. At -7, and here's -4, at -7, our value was 700 of our graph, and at -4, our value was -56, about right there. So the graph can do whatever it wants, la 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 la, but at some point it eventually will have to hit the axis in between these two intervals because it's continuous and we have a point there and a point there. So the answer to the question is yes, there will be a solution between those 2 points. There's one other, so that's one application of the intermediate value theorem, is it can help us hone in on our zeros. That might be useful if you have a function with a lot of zeros and you don't want to bother checking every single one. It could help narrow your choices. Here's another useful application. It's called the Boundless Theorem. And I'm not going to prove it, but it says a polynomial has no zeros above a certain value if dividing synthetically by x minus that value produces a bottom row of non-negative numbers. So there's a lot there. Let's unpack it. Let's say we've got some graph, maybe like this function. And let's say we have some highest value. And the graph goes up infinitely forever, so there's never another zero. If we synthetically divide by this value and get a row of positive numbers, then that means that for sure this is the last value. So that's kind of cool. So let's try. Determine if this polynomial has any zero greater than 1. So let's do it. Let's do synthetic division. 4, 40, 132, 144, and don't forget your placeholder. We don't have a constant term, so I need to put a 0 right there. And let's do 1. So let's see if this is all positive. That's a 4. 1 times 4 is 4. That's 44. 1 times 44 is 44. That'll be 176. 1 times 176 is this. Add those down. 320. That's 320 with a remainder of 320. Do you see how it's all positive down here? So 1 is not a 0 because we don't have a 0 right here. But we know that there's no zeros bigger than 1. So if this was, say, 1 here, and this was 2, it tells us that we have no zeros after that value right there. All of the zeros of this thing are imaginary or smaller than 1. So no zeros for this function bigger than 1. So that's the boundless theorem. You need to know how to do that. It's all about getting this bottom row of positive numbers. We looked at the corollary called Boson's theorem, Bolzano maybe, which says that if you have a negative value and a positive value, there will be a 0 between them if there's a continuous function. And we talked about an application of speeding with the intermediate value theorem. So I hope you enjoyed section 3.4. I bet you liked it better than 3.3 because it was a lot shorter. I will see you in section 3.5. See you there.